All right, welcome back. Today we'll be going over a paper review related to the second paper of two papers related to my master's work, and this one is related to the overview of the uses of high performance size exclusion chromatography in the characterization of natural organic matter in potable water, and we do some additional looking into of ion exchange applications. So this is a work between me and my supervisor back in 2019. Like I said, this is the second paper of a two-parter. So if you did see the previous presentation, that one focused more on the high performance size exclusion chromatography results and the application, as opposed to this is more of an overview on why exactly HPSEC is so useful in water characterization. And with that, we'll just go straight into the abstract here. So just quickly, natural organic matter constitutes the terrestrial and aquatic sources of organic plant material found in water bodies. So if you ever look at a water body and you see a greenish, brownish color, that's most likely due to natural organic matter, which is dead processed plant material. As of recently, an ever-increasing amount of effort is being put towards developing new ways of unraveling the heterogeneous nature of natural organic matter. Heterogeneous being focused term here. We're not looking at one thing in particular. It's a heterogeneous nature just because natural organic matter and carbon-based sources come from so many different parts. They come from animal material versus plants, so that's important consideration. And this is important as NOM is responsible for a wide variety of both direct and indirect effects on potable water, ranging from aesthetic concerns related to taste and odor to issues related to disinfection byproduct formation, which tends to be a known carcinogen, and metal mobility. So the idea that metal can latch onto certain compounds and can pass through the water treatment system. So a better understanding of natural organic matter can also provide us a better appreciation for future treatment design and understanding potable water treatment on specific fractions, on constitution and constituents of natural organic matter. So that's an important thing to mention here, is that we're also looking at specific fractions of this heterogeneous nature and its constituents. And the use of HPSEC has shown a growing promise in its various applications, and that's because we can partition ultraviolet absorbing moieties, not just ultraviolet, but actually also visible wavelength absorbing moieties, into ill-defined groups of humic acids, hydrolysates of humics, low molecular weight acids. And it can also look at absorbance within the UV range, as I said, further providing a spectroscopic fingerprint that is simply unavailable using the surrogate measurements of natural organic matter. And I'll go into both of these later on. So this review mainly focuses on the use of HPSC and the characterization of NOM, although we do focus a lot on the characterization of natural organic matter, and mainly in the potable water setting. So we're not too focused on wastewater in this context. So with that, we'll go straight into it, and we're not going to focus too much on the text. We'll focus on the text where it's relevant, but for the most part, we'll look at a lot of the figures and a lot of the compendium of references that were put together. So we were talking about characterization of natural organic matter, and it's worth mentioning to date what sort of tools we are currently using for characterization. And one thing that we use is something called ultraviolet absorbance at 254 nanometers. So that just says when we pass light through a sample at 254 nanometers, what proportion of that light at 254 nanometers is actually absorbed by the sample. And that's because, and this is also referred to as UVA 254 or UV absorbance. And that's just because things like aromatics in the water tend to absorb at that wavelength. And so it's a surrogate measurement. And that's just because for natural organic matter, because remember, natural organic matter is this sort of compendium, complex, a variety of plant and animal decaying matter. And because it's this decaying matter, what you tend to find is a lot of aromatics. And those aromatics, because of its resonance structure and its extended conjugation, tends to react with a lot of things in the water. So for this reason, if we can find a way to measure that proportion of aromaticity in the water very quickly, then that could provide us a form of characterization. So it's called a surrogate parameter for natural organic matter, because even though natural matter is so complicated, it's one of many tools that we can use. And actually, I say exactly right here, estimation of the aromaticity of the sample. And this is just to say UV has been developed in potable form factors. Potable, but portable actually. And that's just because it's actually a system that we can actually put on the water treatment plant site, and we can teach operators how to use it. And it's something that they can readily record and take a look at. And then we can come back later on and then find out whether natural organic matter or measured via UV254 peaked during certain times of the year or following certain rain-offs. And of course, this is to mention that this does not encompass full heterogeneous norm. It's only a measure of one variable. And one thing that we've done going forward is we've looked at other surrogate measurements, one being SUVA 254. And this is defined as taking the UV absorbance at 254 and divided by the TOC, which is the total organic carbon. So this is a way that we can actually measure exactly how much carbon in terms of milligrams per liter of water, what that mass is in terms of carbon. And that sort of tells us a little something else. Remember, UV254 is the aromaticity, and TOC actually tells you how much carbon actually exists, right? So remember, carbon can actually also exist in aromatic form, and it can also exist as alkanes or long chains, right? So by looking at this, we can actually have we can sort of further characterize our water by saying what proportion of this carbon belongs to aromatics versus a long chain alkane or alkene. And like I said, this is all for a test of aromaticity per unit gram of carbon. And this is just to also follow up with the fact that there's lots of other resources available at disposal, but they're limited to portability and availability. So it's one thing to put a spectrophotometer at the site that an operator can readily use, but it's a whole nother thing to run a TOC apparatus, which requires lab usage and requires expensive equipment and someone to take care of all that. And why, of course, are we concerned with natural organic matter? Well, natural organic matter, here I'll highlight it here. We can trace the presence of certain natural organic matter components with their corresponding DBP product, which is disinfection byproduct. Actually, I translate it right here. These known carcinogens. So we can trace what exactly. So we look at water and we're concerned with these disinfection byproducts. And then we sort of ask ourselves, what are the precursors to these? And can we characterize the water in the best way we can, where we can sort of correlate those surrogate parameters with DBP formation? And ideally, we want it to be as portable as possible so that we can use it on site, but that's not always practical. And that's just because of the heterogeneous nature of natural organic matter. And then I go on to mention the fact that we can use this technique called high performance size exclusion chromatography, which I won't get too much in just because the previous presentation focused a lot on that, the setup and the sort of procedure and methodology of how that is set up. So I'm going to leave that for the other presentation and not quite go over it again. So we can use this natural organic matter, and we can look at natural organic matter reactivity, and we can use HPSEC and other peak identifier techniques to model the formation of these THM species. THM being trihalomethanes, and DBP are disinfection byproducts. THMs are a subset of disinfection byproducts. This just means what are the byproducts of the disinfection process. The THMs is just one of those. So with that, we go a bit into the literature review. I'm going to skip as much of this as possible. What else can I say about this? Well, typically in water treatment, at least in the conventional treatment train, the removal of natural organic matter has been explored using various chemical and physical methods, including carbon-based absorbance, most notably things like activated carbon, forms of oxidation, coagulation, idea that we're coagulating and suspending certain flux within the water. So we're bringing it out of it, making it less soluble so that those larger particles can sort of coagulate together and settle. Additionally, we have things like membrane filtration, where we're just passing it through a porous membrane. Things like ion exchange, which we go a bit more into, and which is the focus of most of my work. And more advanced forms such as electro-oxidation, electrocoagulation, nanotechnologies, biofiltration. And of course, natural organic matter itself has a significant impact on the engineering systems themselves, and that's because they contribute to things like membrane fouling. So the more of these sort of compounds, large compounds they have in the water, well, the faster that you tend to clog certain pores and clog certain filters. And as I mentioned, trihalogenated methanes formation, things like metabolizability, aesthetic concerns, and corrosion. So we sort of revisiting those same issues. Now we go straight into natural organic matter functionalization. So when we're characterizing, we want to know not only what it looks like in terms of its carbon or its aromaticity, but also sort of what are the other components, other functional groups that are associated with this natural organic matter. So here we have the elemental composition as a percent. So most of this work, I'm pretty sure, was carried out using NMR and also FDR analysis for the functionality, and the elemental composition using nuclear magnetic resonance. So we can sort of look at certain percentages here and compare them from between something called humics and fulvic. And these are just two different components of natural organic matter. So we can always further characterize, but even then, these groups tend to have a lot of overlap. So to say that in terms of elemental composition of carbon, humic acids tend to have a larger composition than fulvic acids, not by much. Tends to have larger oxygen, perhaps lower sulfur, aliphatic versus aromatics. So aromatics is what we're concerned with because of UV254, which tend to, as I said, the extended conjugation and residence tends to react with a lot of things in water, so it makes it very problematic. 24% as a function, as opposed to 16, so that's sort of a noticeable difference. And of course, the aliphatic is sort of the opposite. For fulvic, it's larger than humic acid, so there we get to. So here we got more aromatics, let's just say. And then for the aliphatics, we tend to have more long chain alkenes. And then we have things like, because they're more aromatic, perhaps we have more phenolic groups attached versus less so for fulvics. Again, a lot of overlap here. And the methyl groups and the carbonyl groups, there's a lot of overlap there, so it's hard to say. But that's a lot of this overlap has to do with the fact that we're looking at so many studies here. You can count how many there are, and there's probably more than a dozen. And people are looking at different water sources, and within different water sources, you have different compositions. So it's very hard to say exactly how we want to characterize these things. And usually it's the case that we just look at, generally speaking, some functional groups, some characterizations, and then draw these distinctions. But in the end, it's very heterogeneous. It's hard to say one way or another. And then we go more into something called natural organic fractionation, which is just how we can fractionate between humic acids, fulvic acids, and how we can fractionate different molecular weight ranges. So I'll go a bit more into that later on. This is actually the most important table that I want to focus on, which is, so we sort of talked about the functional groups. Now this is the fractionation, where we're looking at the hydrophilicity and also the basicity of the groups, right? So we can always further characterize it in different forms. And this table refers to the component analysis of various water constituents based on hydrophilicity, important thing here, and acidity. So the hydrophilicity just refers to, is it hydrophobic group, is it hydrophilic group? So hydrophobic meaning fear of water, and hydrophilic means favorable towards water. So hydrophobic, you tend to see a lot of aromatics. In the hydrophilic groups, you tend to see more these alkyl groups. So this is just to show that within these fractionations, you can do the hydrophobic versus hydrophilic, the bases versus the acids, certain components. So this is just to say, again, because we're looking at, these are carbon sources from maybe plant or animal matter, what exactly are they? What are they exactly, right? Because a chain just doesn't exist on its own, an aromatic. It exists as part of a larger component, right? So this can be actually proteins and amino acids that belong from decaying animal matter versus other things. You see some fatty acids that belong to the hydrophilic acids, and then the more specific to the functional groups, which all relate back up to here. And then some molecular weight ranges where hydrophobic bases can range upwards to 70,000, along with hydrophobic neutrals. So those can range up to 70,000. So we're talking about very large aromatic chain groups and aromatics attached to one another, versus the hydrophilic neutrals. Again, it all matters where they exactly come from, where you have alcohol and low molecular weight alkyls. What you tend to find is these tend to be of lower molecular weight. So we're also looking at a size distribution as well. And just a few references here just refer to different sources depending on what body of water you're referring to. Again, because it totally matters depending on what region and geography you're looking at. Other research say the hydrophilic acids are the dominant group versus hydrophobic. Very hard to say one way or another. So with that, we'll just skip a lot of this and refer to absorbance indices here. This is an important thing because we talked about the use of UV254 again to look at aromatics. So the thing is, you're not just limited to aromatics and UV254. You can actually look wherever you want in the ultraviolet range. So for example, this is the absorbance at 210 nanometers. And this tends to closely correlate, according to literature, to nitrate concentration, certain activity of microbials, and non-conjugated carboxyl groups. So they tend to all absorb at 210. And then you go to 254, which is what we're familiar with for aromatics. So that kind of makes sense. And there's a lot of literature that sort of supports that. And then go to higher up on the range, and then you tend to get maybe those forms of organic matter that are more likely to add color to your water. So ideally, if you're looking at water and you can visually see it's darker or lighter, well, that might correlate very closely to 270 according to some literature. Carboxylic and aromatics, so they're looking closer to 210. DOC concentration, this is a little hard to say just because looking at these absorbances, again, these tell you about more the functional and the composition of the water. It doesn't actually tell you about the amount of carbon in the water, but some have looked at DOC concentration and DOC aromatics as being a function of these ranges. Additionally, we have things like SUVA, which I had mentioned again is UV absorbance all over TOC. So if we were to look at it for 255, we can sort of see, well, when this goes up, we tend to find an increase in dissolved organic matter, molecular weight fractions, also the ratio of fulvic acids to humic acids. There's actually quite a lot there. SUV 254, again, the aromatics, well, it tells you a lot about the hydrophobics and aromatics, and also disinfection byproducts. So this is probably one of the more important, for our purposes, related to disinfection byproducts measures, which is the aromatics and also SUVA 254. And there's a lot of literature that sort of supports this to be the case. And also you can actually look at specific SUVAs and take the ratios of other SUVA parameters and then correlate it somehow to lignin derivatives and aromatics. So you can sort of go more into that as well. And then as you can use one specific absorbance, you can actually take the ratio of absorbances, and all of a sudden you have some other forms of characterization, not just aromaticity, but okay, well, maybe we get some information about disinfection byproduct formation. Maybe the phenolic content is maybe really sensitive at 203 nanometers. So that's of importance to us. Some relation due to size. So the reason how it can be related due to size is, so you see, I see some UV absorbances at 250 here, which is again the aromatics, but also at 410 and 365, maybe those ranges are dominated by very large dissolved organic matter fractions. So that sort of tells us that if our samples absorb at these very high wavelengths, close to 410, 365, well, that tells us that we have large fractions. And if there's a high UV 254, well, it tells us that it has large aromaticity. So again, we're just characterizing by looking at different absorbances and then sort of taking the ratios of that. So there's a lot here. Again, these are all very, weak forms of characterization, but they're there and they're fairly easy to use and easy to train an operator on. It's something of importance for us. This goes into something called ultraviolet absorbance and excitation emission matrices. These are more a little complicated. I'm going to skip that for now. The instrumental analysis of NOM is something that I went quite into depth in the previous presentation. So for that, I actually would refer you to the previous presentation on that, the two-parter for this. High performance size exclusion chromatography. That's a mouthful. I should probably just refer to as HPSEC. I do go into it a bit again in the previous presentation, so I'm going to skip it for that reason. I do go into this image in the other presentation as well, but it's interesting to note that again we're looking at different hydrophilic, hydrophobic acids, large, small. So here's low molecular weight acids here, and humics, referring to humic acids. So why is this of concern to us? Well, again, we're looking at size as a function of also functionalization and different forms of characterization. So this is just interesting to note that if we are concerned with, say, something like only humics, what sort of ranges can we expect that they would exist in? So we can sort of take right here, this big range here, which comes between 10 to the 3 and 10 to the 4, so about 1,000 to 10,000, and this is log, so this could be like 20,000 or so. What you tend to see is that the humic substances tend to dominate this sort of range, and these letters here just refer to different sources in the literature, so there's sort of a general agreement. But at the same time, the low molecular weight acids and building blocks, give or take, they sort of exist somewhere in this range from 100 to 1,000. Again, it totally depends on your water body. And then you have these large biopolymers. But for our concern, because we're focused on the natural organic matter and those species that tend to form disinfection byproducts, it tends to be the humic substances, which is another word for like humic acids in a way, that all exist somewhere in this range. So again, all forms of characterization and your water source, it varies. Going a bit down here, we want to know, okay, so given these apparent molecular weights, how important is it? What sort of literature has been done where they looked at specific fractions of these and correlated with other things of concern? So as one example here, by the work of Liu et al. 2014, what they noted was certain soluble microbial products were responsible for the bulk of natural organic matter in potable treatment, and that very low components, less than 1,000 daltons, were actually responsible for 85% of the organic carbon pool. So this would be measured by the dissolved organic carbon or total organic carbon, and actually 65% of all DBP precursors. So that just shows us that according to this literature, that these soluble microbial products were responsible for a big part of the carbon pool, and those that were most reactive. So that tells us a little something. Additionally, we have here the earliest work identified low molecular weight compounds, less than 500, with actually the largest formation of these things called HAAs, which are haloacetic acids, which are another subset of disinfection byproducts. So we're concerned with underneath disinfection byproducts, haloacetic acids and trihalomethanes. These are just one form. So why hydrophobic NOM, natural organic matter, has been heavily tied to the formation of known DBPs. At least with this particular work, they identified hydrophobics as being responsible for 80% of all unknown disinfection byproducts. And I can't quite remember from this paper how they actually found out about unknown disinfection byproducts. I kind of remember what the paper had looked like, but it's sort of been years since I had looked at it. Like how exactly can you actually find an unknown disinfection byproduct if it's unknown? But that was some interesting work. And again, they're looking at certain molecular weight ranges. So here's another one where, well, you know, the exact molecular range targeted by coagulation. This is important because, again, we're looking at characterization, but we're also trying to implement something within a water treatment train, right? So if coagulation can target a certain subset, well, that sort of tells us that that subset won't exist in later, when it's removed from the water, when it's faced a nanofiltration membrane, that subset is actually gone, right? So we can actually use it as pre-treatment for a more expensive form of treatment later on. And this sort of says that the coagulation, what exactly the range that it targets is up for debate, but those tested with alum as a coagulant has shown to leave the AMW components within the range of 150 to 3K daltons, and that just tells us anything larger than 3K daltons tend to flock better and settle, and therefore it actually won't make it all the way to the later stage nanofiltration or ultrafiltration system. And also, even this work by Zhang et al. 2016 noted that the bulk of the removal was between this 1 to 3K dalton range. So 1 to 3K dalton here is right between here, 1 to 3K, 1, 2, 3. So sort of this bulk range right here, right? So here, even coagulation is really targeting a big subset of the humics as well. And that's sort of the reason why even treatment with coagulation, which tends to be fairly cost effective, does remove a bulk of the natural organic matter along with the formation of disinfection byproducts, which is good. And then later on, this sort of part of the paper just goes a bit more into the ion exchange resins and the applications and some information about the resin properties. So here I have a bit of an overview on some of the formation of these resins and why they're important to us. So these resins are ion exchange resins, and the reason why they're ion exchange is because they're sort of attached to a stationary phase on a resin. And then what happens is you can even get quaternary amines, tertiary amines, or secondary amines, and these are strong base ion exchange. You can also have strong acidic ion exchange. But for our purposes, one of the things we want to remove are these acids in the groups. And that's because earlier on we noted that humic acids, substances, tend to be hydrophobic acids. So we're trying to remove these negative charges from these groups. And in order to do so, we use these amine groups. And how this works is that depending on if it's a quaternary, tertiary, or secondary, by this functionalization, you sort of have this positive charge on this amine group. And then you sort of have a chlorine attached, like loosely attached. And then ideally, when you have a mobile phase that constitutes your water, passes through these resins, it actually will exchange with that chlorine atom attached to these amine groups. The humic acids actually attach to the resin itself, so it actually gets attached here. So let me just write that here. So normally this would be a Cl minus, and then you have the water that comes through, and then the Cl minus attaches to something like carboxylic group. Carboxylic group that's attached to something that's a very highly aromatic humic acid, right? And then the humic acid sort of attaches to the amine group, and then what's left over is the Cl minus that passes through the water, and that's why you have brine as a byproduct following ion exchange, at least for strong base ion exchange. And the reason why I have sort of these depictions here is that in Resin Properties, I talk a little bit about how the formation of these ion exchange actually works. So you have this copolymerization between these DVB, which tends to be, this divinylbenzene tends to make up the most part all the resin backbones. And so you have this copolymerization where you get this sort of like lattice structure a bit here. And then following this functionalization at certain conditions, you can actually take these groups and then add our functional amine groups that we want on them. So ultimately, this is how these strong base ion exchange resins actually work. You sort of form this backbone, and then you functionalize it with whatever primary or secondary amine group that you want, and then all of a sudden you have an ion exchange resin as a result. And the other thing I had wanted to mention was looking a bit into resin properties. There's a few things related to decreased cross-linking leads to an increase in the fraction of total porosity contributed by mesopores. So not only do we have actually functional groups here, but there's actually a bit of a lattice structure here where you do have groups that can actually get caught within the, it's actually technically not a lattice structure because lattice is more for at the atom level, but you sort of have the structure where components, there's a bit of porosity that matters. And there was a thing related to steric effects. The reason for this phenomenon is that cross-linking opposes osmotic forces caused by the exchange of ions with large hydrated radii. That's just to say when a component, some form of, let's just say, humic acids actually comes through the water, you're not just actually dealing with the humic acids itself. You're dealing with it circulated with water atoms, and as a result, it makes the radius larger than you'd expect. And so this is an indirect mechanism by which the selectivity of compounds can be affected simply through the steric and physical effects. So we're not just concerned with ion exchange, which would be a physical effect, but the steric effects refer to actually the size. And yeah, so that seems to be good for that fold, for that section. Strong basicity, exchange with the weakest of salts. So whether you have weak or strong actually will tell you that if you have strong quaternary amine groups, you tend to be able to even exchange with the weakest acids, as opposed to if you just have a secondary, this positive charge isn't as strong, right? So then you only have the strongest acids. Let's just say a carboxylic acid just by itself will readily exchange with the resin here. But if you have the stronger bases, well, what happens is that Cl minus readily jumps off, and even weak acids are much more easily to latch onto ion exchange resin. So there's a little bit about membrane fouling as prime consideration, and the fact that NOM can actually take advantage of that. And then the rest of the literature review goes a bit more into MIAX, which is a form of magnetic ion exchange, which is sort of a technique that I think has not stood the test of time from what I understood. But yeah, and then the rest is just the references for the work. So with that, thank you everybody for watching. If you have any questions, just make sure to leave a comment. For those sections that I had sort of skipped over related to HPSEC and other forms of characterization, I refer to you to the second part of the sort of series where I look where I do a review of the second paper. And with that, I thank everybody for watching.